Hello, this is the first part of the chapter 3.2, and we continue to talk about the determinants and how to calculate them. And last time I figured out how to calculate determinant of matrix of any signs, and we will continue doing this today. But first, let's just look some properties of determinants which makes this kind of calculations easier. For example, a very convenient property of determinant is that the determinant of the matrix would be the same for when this matrix is transposed. So let's just try to confirm it using very, very simple matrix. For example, we have this 1, 2, 3, 4 matrix. Let's compute a determinant and confirm that the transposition doesn't change it. Okay, so here it's 2 by 2 matrix, so our determinant is just the difference between the product of two diagonal elements. So we multiply two elements of left diagonals, 1 and 4, give us 4. We multiply two elements of the right diagonal, 3 and 2 would give it 6, and we end up with value of our determinant -2. Great. So now let's conduct calculation for determinant when we transpose the matrix, which would basically replace row and the columns. So, and our left diagonal elements will remain the same, but the right diagonal is just flipped. And of course, because we just dealing with a product, we are having exactly the same value for the determinants, still -2. And you can go at the end of the chapter and confirm it with a couple of examples of larger transposed matrix. And you will see that in a case of 3, 4, or any size matrix, the determinant of the matrix and its transposed will be exactly the same. Okay, so that's really nice. Let's see what kind of other properties we can have, or maybe to make our calculations easier. Okay, and the row operations is a very, very, very important part of these calculations, because we discovered in last lecture that when we have a triangular matrix, the determinant calculations is so easy. We just multiply the diagonal elements. Wouldn't it be nice to reduce our matrix to echelon form, and hopefully we'll get a triagonal matrix, and then our life will be easier. So let's see what's happened when we apply the row operations to our matrix. And the good news, the property number A of the theorem 3 telling us that if we perform our favorite operation, when we take one of the row, multiplied and added to another one, our determinant remain exactly the same. And again, let's just try to confirm the property using our very simple matrix. Let's say we take this matrix, we're calculating the determinant, and we want to reduce it to the echelon form. And of course, our first order of business will be get rid of this 3 over there and get 0 instead. So we will take our first row, multiplied by 3, and subtract it from the second one. And our theorem 3a tells us that the determinant will be the same. So let's try to calculate it. And again, I'm just performing this calculation here very carefully, because, you know, this is the first time we're doing this. And you're always careful first time you're doing this. We don't cut any corners. So we end up with this nice echelon matrix, because it's only 2 by 2 matrix. It has only 1 0. Let's calculate its determinant and see if it's indeed going to be -2. And lucky us, we get -2 from the product of the left diagonal and the right diagonal goes to 0. So yes, determinant is still -2. So property A holds. What other properties we can have? Row exchange. We know that we often need to exchange the two rows in the matrix. And this is where you have to be very, very careful. Yes, we can change the rows in the column, but then we will put our determinant with a negative sign. Okay, let's try to confirm it with our simple matrix here. Let's say we want to exchange row first and second, and we will see if determinant indeed will have a with a negative sign would work. Okay, so let's just do that. So we are exchange the order of our column, and we are putting the negative in front of it to follow the property B. Okay, so again, we just calculate the product of our diagonal elements. So, and indeed, again, we get -2, exactly the same determinant as we have in 3 cases before. So, okay, that seems to be working. There is one last properties which you have to remember for determinant. If we have one of our rows multiplied by the constant, any constant, say constant k, we can factor it out from the determinant and write it down, the constant k times the determinant. Okay, let's see how it works in our simple matrix. Let's just say we are taking the first row and we will write it down as the product of number 2 and the proper element of the column. For example, instead of 1, we will write it down as a 2 times 0.5. Instead of 2, we'll write it down as 2.1. So now our property C tells us that we can factor out number 2. Let's just do it. So we end up 2 times determinant of the matrix with a half of the first row. Let's compute a determinant and see if we still get -2. So far, we were very lucky. And again, here in parentheses is the calculation for our determinant. Our left diagonal product is 0.5 times 4, which gives us 2. Our right diagonal is 3 times 1. So indeed, here in parentheses, we have a -1 multiplying by 2 will still get -2. So all these properties seems to be holding. So now, if we want to calculate the determinant of any matrix by reducing to the echelon form, all we have to do is just be very careful to these 3 properties and carry out our calculations. Let's do it with this matrix A, so which is 3 by 3 matrix. So instead of reducing to 3 2 by 2 matrices, we will try to reduce it to the triangular matrix and just calculate its determinant this way. Okay, so and hopefully this matrix will be easy and we can go ahead and just multiply diagonal elements. Okay, here is our determinant, and I'm just writing it down as a straight bar form just to avoid repeating det here. Okay, so let's try to reduce it as an echelon form, and as usual, we start with the second row. Instead of -2, we want to have 0. So we take the first column, multiply by 2, and subtract from the second, and nicely we have a zeros here. Then we're going to the third element of the first column, and again, instead of -1, we have 0. We want to have 0 here. So we take a first row and add it to the third one. And that's give us nice 0. And look, we even get lucky here because our second row actually have 2 zeros in a row. So if we exchange the second and a third row, we pretty much will have an echelon form. So let's do it, but let's keep in mind the property B, which tells us that if we are exchanging 2 rows, we have to multiply our determinant by -1. So we have, please be very, very careful. One of you at some point will forget it. Minus signs are very important here. Okay, so look at us now. Now we have a nice non-zero diagonal element, and below it, it's all zeros. So we have a triangular matrix. And the previous chapter will tell us that if we have a triangular matrix, we'll just multiply our diagonal elements, and that's our determinant. So let's just do this, and that's give us a value equal 15, which we received without, no harder calculation than reducing to echelon form and multiplying 3 numbers. So now I would like you to go back to the end of the chapter 3.2 and try to calculate several more metrics by reducing them to the echelon form.